Assalamu alaikum. Hi everyone. So in this video I would like to share firstly how to find the Fourier series coefficients of periodic functions using Matlab, and secondly how to show the evolutions from the fundamental components of the functions, which evolves by using superpositions. By adding the harmonics, we can show that it evolves into the original functions. Okay, before that, we have to be familiar with the integral function or command. Okay, let's begin with a simple example. Suppose that I have two functions. The first function is f equals to t squared. The second function is, let's say, f equals to sine t. So if I write f1, let's say, equals to t squared, I will get this error message in which the variable t is undefined. So I have to declare or specify the variable t before I begin with the to describe the functions. So in this case, instead of defining t as an array or constant, we will use this symbolic declaration for the variable, because we intend to use the integral functions. So before we define the functions, we have to declare t as a symbolic variable, in which we have to write syms space t and enter. Okay, now as you can see, the variable t appear in the workspace, in which t is defined as 1 by 1 symbolic variable. Okay, then I can write my f1 equals to t squared, and let's say f2 equals to sine t. Alright, then I want to integrate my f1 from let's say 0 to 5. So how do we do that is, I can write, let's say I introduce another variable, p1 equals to int, stand for integral f1, integrate f1 with respect to t, comma, from 0 to 5. So I hit enter. So the answer is 125 over 3. If you notice, even the value for p1, which is the answer for the integral, is regarded as the symbolic value, even though it is obviously a constant. So we have to change the symbolic value of p1 to the numeric value by using the symbolic to numeric conversion. So one of them is by using the double command. So I can write p1 equals to double p1. So now if I hit enter, I get p1 as a numeric value, which is 41.6667. Okay, next I want to integrate f2. Before that, let me clear the command window. I want to integrate f2 because f2 is equal to sine t. f2 equal to sine t. I want to integrate f2 with respect to t from 0 to pi. So pi in Matlab is pi. So Matlab gives the answer equals to 2. Equals to 2. P2 equals to 2. But again, P2 is regarded as the symbolic. So we have to convert the format of P2 into symbolic to numeric by using the double command. So sorry, my mistakes. So I have P2 equals to numeric value 2, which is shown in workspace. So now we are ready to compute the Fourier series coefficients of a functions. Before that, let us clear the command window. Okay, let's recall the Fourier series formulations. If we refer to the textbook, so this is the formula or the form of the Fourier series. So we have three coefficients, a0, an, and bn. So these are the formula for a0, which involve the integrals an and bn. So suppose that I want to find the Fourier series for the functions, for this function. So this function is defined as from 0 to 1, f equals to 1. So when t within 1 to 2, f equals to 0. The period of this function is 2. Okay, so I can calculate the coefficients a0, an, and bn by using Matlab. Okay, let us clear our workspace because we want to start fresh. Okay, so we first we have to declare the symbolic. We declare t as a symbolic variable. Okay, next I want to write my functions. So my function is this. If I take one period from 0 to 2, so my f equals to 1 when t is from 0 to 1, and my f equals to 0 when t between 1 to 2. Or I can write my function in the form of unit step functions. Okay, if you remember, that function can be written as, let's say, f equals to unit step t minus u t minus 1. Okay, but in Matlab, the unit step function is not as simple as ut. It has the special built-in function which is known as Heaviside function. So we replace the u with Heaviside and we hit enter. So we get this, f equals to unit step t minus unit step t minus 1. Okay, to check our graph, we can plot the function by using the command easyplot f. So we can set the range for t, let's say from 0 space 2, meaning that I want to plot f in the range of t between 0 and 2. So I have this graph. Okay, so now let's proceed with the calculation of the coefficients. So I begin with a0. So a0 equals to 1 over t, integrate the function with respect to t from 0 to t, capital T, which is the period. Okay, so our period equals to 2, obviously. Okay, so I can write a0, but we know that this a0 will become the symbolic variable. So we can maybe we can write it slightly different, because we know that a0 is symbolic. So I write in this manner, a0 underscore sym equals to 1 over t, the formula for a0, times integrate the function ft, the function f, with respect to t, comma, from 0 to period t. So the answer is 1 over 2. Okay, again, A0 sim is a symbolic value. So to change it to a numeric value, I write A0 equals to double A0 symbolic. So I get the real value for A0. Okay, let's proceed with the AN. So AN is defined by this formula. So if you notice, we have another symbolic variable which is n, and we have a constant omega naught. As for the constant, it's not a big issue because omega naught is equal to 2 pi over period. But for n, we have to declare n as the symbolic if we want. But actually, we can replace n straightforwardly with the numeric value. So if I want to find A1, so my n equals to 1. If I want to find A2, my n equals to 2, and so on. So if I want to find A1, I need to write A1 equals to 2 over, sorry, before that, let's define the omega naught. Omega naught equals to 2 times pi over capital T. So this is the value. So now A1 equals to 2 over T times integral braces F times cos n omega naught T. In this case, n equals to 1 because I want to find A1. Cos 1 omega naught T. Okay. Integrate with respect to T from 0 to capital T. So I get A1, which is equals to 0. By the way, A1 is again a symbolic value. We have to convert the value for A1, symbolic value of A1 into the its numeric value. And then I can repeat A2 equals to this 2 over T integral F times cos 2 omega naught T, and the answer is 0 as well. And then A3 3 3. Okay, so apparently all value for AN seems equal to 0. Never mind. So we can proceed with BN. So now I want to find B1. So B1 equals to 2 over T times the integral of F times sine 1 times omega naught times T. Integral this function with respect to T from 0 to capital T. So the answer is 2 over pi for B1. Next, B2. So B2, I can change 1 to 2, so I get 0. For B3, I can change like this, so I have 2 over 3 pi. Okay, again, all coefficients A1, A2, A3, B1, B2, B3, all of them are symbolic value. Okay, now instead of working in the command window, we want to work in the script, which is more convenient. So suppose that I want to find A1, A2, A3 up to A10 and B1, B2 up to B10. So before that, open the new script, and then we have to maybe we can define everything starting from t, and then the function f, the period, and the fundamental frequency. So so we declare the symbolic variable for t, and then our period equals to 2, our fundamental angular frequency equals to 2 pi over t, and then our function f equals to heaviside t minus heaviside t minus 1. Okay, and then we get a naught equals to 1 over t times integral f with respect to t from 0 to t. This is an, so we change f to f times cos n omega naught t, and bn is 2 over t times integral f times sine n omega naught t, integral with respect to t from 0 to capital T. Okay, as I mentioned before, a naught, an, and bn will become the symbolic variable. So before that, instead of writing a1, a2, a3, and so on over and over again, we can use the for loop. So if I wish to have a1 up to a10, I can use for loop. For example, for n from 1 to 10. Okay, so my a braces n equals to this, my bn equals to this one. So I end my for loop, so I can get a1, a2, a3 up to a10, and also b1, b2, b2 up to b10. Okay, let's see what happens if we run this script. So click run. Let's name this script. For example, Fourier Series coefficient. It's running now. If you check the status, Matlab shows that now it is busy because it is running our file. We have to wait maybe 1 or 2 minutes. Okay, so we get the answer. So now A is a 1 by 10 symbolic variable. So we don't like this kind of symbolic value because we want the numeric value. So we have to change the value of A and B from symbolic to numeric. So we rename this as A symbolic, B underscore SYM, and then the numeric value, the real numeric value is AN equals to double A symbolic. and we write the same statement for B. Even for A0 we can write something like this. So the real A0 equals to double A0 symbolic. Okay. Okay, let's rerun our script. Maybe we can begin with clear and CLC, but these two are optional. So we have the coefficient an and bn, in which the value of an and bn are numeric. I think there is a mistake, because the coefficient b is supposed not equal to 0. Here, sorry, my mistake. So this is bn equal to double b symbolic n. So rerun everything. So we have this. So for an, all of them are 0, from a1 to a10. For bn, these are the value. This is b1, b2, b3, b4, up to b10. So in other words, we can interpret this data when n equals to odd value, there is a non-zero value for bn. When n equals to even value, bn equals to 0, as you can see in here. Alright, so can we use this idea to create a functions that can afford any periodic functions, for example? Okay, now suppose that we create a function that calculates the Fourier series coefficients, and the user need to define first the functions, second the period of the functions, and third up to how many harmonics that they wish to have. So by creating a new functions, and we place our file side by side with the function that we want to create it. So we can copy these things and edit somewhere which is required. So suppose that our function name is Fourier series. Okay, so user need to provide the following input, which is the functions. The user need to define what is f, the period of the functions, and up to how many harmonics, let's say capital N. So we will provide the answer, which is the coefficients of the Fourier series. The first a0, second an, second bn. Okay, so instead of fixing this value 1 to 10, we can change this to n. So user will decide how many n that he or she required. So no need to change anything here, and that's all. So for n and n. So we can save this and name our file with the same name of our functions. So we can close this. Okay, so if I clear everything, I want to use this new function, Fourier series. So now we want to edit our M file. So we wish to utilize this Fourier series function that we just created. So we can remove this redundant statement, because now we have this. function. So we can write a naught comma b, comma a comma b equals to Fourier series. Okay, now we are recalling this function, braces f comma t comma n. So now we have specified our f, which is this function. Our capital T is equals to 2, which is the period, and now we need to specify the number of harmonics that we desire. So we can write n equals to, let's say we wish to have more harmonics, we write n equals to 50. So if we run this file up to this stage, okay, so we have the coefficient of a and b now, the size of a and b are 1 by 50 because we have 50 harmonics, meaning that we have a1 up to a50 and b1 up to b50. Okay, so next we wish to demonstrate visually how the function f evolved from the fundamental components into the complete functions. So we wish to add, let's say, f equals to a naught plus a1 cos 1 omega naught t plus b1 sine 1 omega naught t, and then plus again a2 cos 2 omega naught t plus b2 sine 2 omega naught t up to plus up to a50 and b50. And we want to show maybe some animation how the signal evolves from the fundamental components up to the original functions. Okay, for that purpose, since we are going to plot the numeric graph of f versus t, we have to introduce the numerical value for f and t. Since we have this symbolic variable t, we can write in a quite different manner. So let's say this is our t for the purpose of plotting the graph. So t num, for example, which stands for numeric value for t, equals to 0.01. Let's say we wish to have 3 cycles. We want to show 3 cycles of the signal. So it will be 6 seconds. And we need also to introduce the numeric value for our function f num. By the way, we begin with the initial value for f num. Let's say a naught. A naught is the DC component of the function, so we begin with a naught. Okay, now we can introduce the for loop, because we are going to add the harmonics one by one, all over again, until the 50th harmonics. So we can write for n equals to 1 up to n, capital N, which is 50. So let's say harmonic equals to an times cos n omega naught t num plus bn times sine n omega naught t num. Okay, so f num, we want to update our numeric functions equals to the previous numeric value for f plus the harmonics, the current harmonics. And then we can plot our graph. Plot t num f num, which is plotting function f versus t, the numeric their numeric value. And we can end this for loop with end. Okay, now if we run our code up to this stage, so we get this graph, which is almost identical to the original graph, like in the textbook. So since we specify the length for tnum up to 6 seconds, it shows 3 complete cycles of the square wave with what do you call the average value as 0.5, because our a naught equals to 0.5. By the way, we could not see the animations, the evolution from fundamental up to the higher harmonics, because the plotting occurs too fast. So we have to place one statement that pause our plotting. So the command is pause, maybe for 0.1 second, and then we rerun our code. Hopefully this time we can see the animation of the graph. Now, okay, so we have demonstrate the animation of the graph from fundamental up to higher harmonics. If you wish to make it even slower, you can increase the value for pause. One cycle, maybe we can up to 0.2 seconds delay. So if I rerun this code, so the animation becomes slower than previous, and it reached to the 50th harmonics. So to wrap up everything, so this is how do we create the animation of the evolution for periodic functions that show the computation of the harmonics and the addition or superposition of one harmonics up to higher harmonics. So first of all, we create the Fourier series function, and then we make use of the function in our M file, and we create the for loop to demonstrate the animations. Okay, so that's all for now. Thanks for watching.